For 29 days, we lost sight of it. 3I Atlas, an object from interstellar space, disappeared behind the Sun during solar conjunction. New data now confirms that when it emerged, something had changed. Its trajectory had shifted, just enough. Just precisely enough to aim it at Jupiter's Hill sphere, the gravitational boundary where orbit becomes possible. Scientists calculate the odds of this happening randomly at 1 in 26,000. But here's what keeps astronomers awake at night. The only efficient time to perform such a manoeuvre is exactly when no one can see you. Near the Sun, moving fast, hidden. Avi Loeb calls it a mothership deployment, and if he's right, Jupiter is about to get very crowded. Keep watching, because what arrives in March might be watching back. If you're as captivated by this unfolding mystery as I am, go ahead and hit that like button and subscribe. You won't want to miss what happens next as we track this in real time toward March 2026. Leave a comment telling me where you're watching from, what time it is in your part of the world, and what you think of this new development. Part 1. The Keyhole Revelation. The Trajectory. We weren't supposed to see. You know that feeling when you catch someone mid-action, doing something they thought no one was watching? That split second when they realise they've been seen? We might be having that moment right now. Not with a person, with something from outside our solar system. The object we call 3I Atlas isn't just passing through our cosmic neighbourhood on a sightseeing tour, it's going somewhere specific, and we've finally figured out exactly where. The destination, the edge of Jupiter's gravitational dominance zone, what scientists call the Hill sphere, the invisible boundary where Jupiter's gravity wins over the Sun's, where a visitor stops being a passerby and becomes an occupant. Here's where it gets uncomfortable. Harvard astronomer Avi Loeb ran the numbers. Jupiter's Hill radius on March 16th, 2026 will be approximately 53.502 million kilometres. That's the size of the capture zone, the gravitational net. Now look at what JPL Horizons calculated for 3I Atlas. Its closest approach to Jupiter, 53.445 million kilometres on the same date. The difference between those two numbers is about 60,000 kilometres. In the scale of planetary mechanics, that's not a near miss. That's threading a needle from across the solar system. Let me put that in perspective for you. Imagine standing in New York and throwing a dart that lands in the bullseye of a target in Los Angeles, while blindfolded, in a hurricane. That's roughly the level of precision we're looking at here. The probability of this happening by random chance, according to the calculations, is about 1 in 26,000. Those aren't lottery odds, those are suspicion odds. This narrow zone around Jupiter, this keyhole, it's not just any patch of space, it's the sweet spot. If you wanted to enter orbit around Jupiter without using massive amounts of fuel, without announcing your presence with the obvious burn, this is where you'd aim. You drift into the Hill sphere at just the right angle, at just the right speed, and Jupiter's gravity does the rest. It's elegant, it's efficient, and according to some, it might be exactly what we're witnessing. But here's the part that makes your skin crawl. 3I Atlas didn't start out on this trajectory. When astronomers first spotted it and calculated its path, it wasn't headed for this keyhole. Something changed. During the period when it passed behind the Sun, when we couldn't see it for about a month, its trajectory shifted. Just enough. The shift required what scientists call a non-gravitational acceleration. A push of about 5 times 10 to the negative 7th astronomical units per day squared. Tiny. Nearly imperceptible. But applied at the right moment, near the Sun where orbital speeds are highest, that tiny push produces enormous downstream effects. This is what engineers call the Oberth effect. When you're moving fast through a gravitational well, even a small change in velocity translates to huge changes in your final trajectory. It's orbital mechanics multiplication, and the only time you could pull this off efficiently, the only window where such a small burn would produce this result, was precisely when 3I Atlas was hidden behind the Sun, when no one was watching. Avi Loeb calls this the mothership manoeuvre. The idea is simple and terrifying in its implications. You don't fly an entire vessel into the inner solar system where everyone can see you. You don't announce yourself. Instead, you aim for the outskirts, for the gravitational fortress of the largest planet, and you set up shop there. You drop off whatever you brought, probes, sensors, watchers. Then maybe you leave, or maybe you stay. parked in an orbit we haven't checked carefully enough. Now, I should tell you that not everyone agrees with this interpretation. Some scientists argue that the precision we're seeing could be the result of refined measurements, updated models, natural outgassing that just happened to push in the right direction. They caution against jumping to conclusions. They remind us that comets do weird things, that orbital mechanics is complex, that coincidences happen. And they're not wrong to be cautious. Science demands skepticism. But science also demands that we follow the data wherever it leads, even when it leads somewhere uncomfortable. The mainstream response has been measured. Careful. Some researchers point out that the uncertainties in the measurements could shift over time, that what looks like a perfect match now might look less perfect with more data. Others note that we've never seen an interstellar object behave quite like this before, so we don't have a baseline for what's normal and what's not. Fair points, all of them. But those points don't explain why the correction happened behind the sun. They don't explain the timing. They don't explain why the deviation moved the object toward the keyhole rather than away from it. If this is natural, it's the most convenient accident in astronomical history. If it's not natural, then we need to start asking very different questions. Questions about intent, about capability, about what happens next. Because here's the thing that keeps astronomers up at night. If 3i Atlas is headed for Jupiter's Hill sphere with this level of precision, it's not arriving empty-handed. Objects don't cross interstellar space for millions of years just to take a quick look and leave. If something made this journey, if something performed this maneuver, it came here to do something. And Jupiter, with its massive gravity well, its rich system of moons, its commanding position in the outer solar system, would be the perfect staging ground. We're about to find out if we've been looking at a rock or a chess piece. Part 2. The Hidden Burn. What happened? Behind the sun. There's a period in every heist movie where the camera goes dark. The protagonists slip into the vault while security looks the other way. By the time anyone notices the deed is done, 3i Atlas had its own blackout period, and when the lights came back on, something had changed. The timeline matters here. 3i Atlas reached perihelion, its closest point to the sun, around October 30th, 2025. At that moment, it was about 1.4 astronomical units from the sun. Closer than Mars, but not dangerously close. For Earth-based telescopes, though, it might as well have been on the other side of a brick wall. When an object passes near the sun from our perspective, the glare makes observation impossible. You can't point your telescope at something that's sitting next to a billion-watt floodlight. For 3i Atlas, this blackout lasted approximately 29 to 35 days, depending on which observatory you ask and what their cutoff for usable data was. During that time, the object was invisible. No tracking, no imaging, no spectroscopy. It flew through the most critical part of its journey in complete observational silence. Before it went dark, astronomers had calculated its orbit assuming only gravitational forces. The sun pulls, the planets tug slightly, the object follows a predictable path. Standard physics. When 3i Atlas emerged from behind the sun and observations resumed, something was off. The predictions didn't match reality. The object wasn't where it should have been. Not by much, but enough. Enough that the models had to be revised. Enough that scientists had to add a new term to the equations. A non-gravitational acceleration term. Let me explain what that means in plain language. Gravitational acceleration is clean, predictable. You can calculate it with certainty if you know the masses and distances involved. Non-gravitational acceleration is messier. It means something pushed on the object besides gravity. For comets, this usually means outgassing. When ice on the surface heats up and vaporizes, it jets away from the comet, and Newton's third law kicks in. Every action has an equal and opposite reaction. The gas goes one way, the comet nudges the other way. But here's where it gets interesting. The non-gravitational acceleration measured for 3i Atlas is about 5 times 10 to the negative 7th astronomical units per day squared. That's tiny, imperceptible if you're watching day to day, but integrated over weeks, over months, it adds up, and the direction matters. The push wasn't random. It wasn't in some arbitrary direction that happens to be where the sun heated the surface. The push was aligned almost perfectly with the vector needed to shift the object toward Jupiter's keyhole. This is where Avi Loeb and others start raising eyebrows. Natural outgassing is chaotic. Comets tumble. They have irregular shapes. They heat unevenly. The jets fire in bursts in different directions as the comet rotates. You get a net acceleration, sure, but it's noisy. It wobbles. What we're seeing with 3i Atlas is too clean, too targeted. The acceleration vector points where it needs to point, and the timing, that's the kicker. The timing aligns perfectly with when the object was hidden. If you wanted to perform a course correction without being seen, this is exactly how you'd do it. You'd wait until you were behind the sun. You'd apply thrust when you're moving fastest near perihelion, because that's when the Oberth effect gives you the most bang for your buck. A small burn at high speed translates to a huge change in trajectory downstream. Orbital mechanics rewards patience and precision. And whoever or whatever corrected 3i Atlas's course showed both. Now, let's pump the brakes for a second. The scientific community isn't sold on this interpretation. Many comet scientists argue that what we're seeing is well within the bounds of natural behaviour. They point out that we don't fully understand how interstellar objects outgoes. These things have been travelling through the cold of space for millions of years. They're not like the comets we're used to. Maybe their composition is different. Maybe they hold onto volatiles in unexpected ways. Maybe when they hit the heat of the inner solar system, they release gas in patterns we haven't seen before. Some researchers also suggest that the apparent precision could be an artifact of how we're modelling the data. When you refine an orbit based on new observations, you're essentially curve-fitting. You're tweaking the parameters until the model matches what you see. Maybe we're overinterpreting the match. Maybe the keyhole alignment is a consequence of how we're processing the measurements rather than a reflection of physical reality. These are legitimate scientific concerns, and I want to be clear, we don't have proof of anything artificial here. What we have is a pattern that's difficult to explain naturally, a pattern that fits an artificial explanation uncomfortably well. There's another piece of evidence that's harder to dismiss. After 3i Atlas emerged from behind the sun, several observatories captured images showing jets, visible structures extending from the object. Now, jets are normal for comets, but Loeb and his colleagues argue that the orientation and strength of these jets are consistent with a directed manoeuvre rather than random outgassing. They suggest that what we're seeing might be the exhaust of whatever pushed the object onto its new course. Again, this is contested. Other scientists see the same images and interpret them as typical cometary activity. Without spectroscopy of the jets, without detailed composition analysis, we can't say for sure. What we can say is that the jets appeared right when we'd expect them if a burn had occurred, and they appeared right when the object's trajectory shifted. The implication here is staggering. If 3i Atlas performed a hidden manoeuvre, if it timed that manoeuvre to coincide with the observational blackout, then this object is not just drifting, it's navigating, it's executing a plan. And if it's executing a plan, then someone or something made that plan, which means we're not alone. And more unsettling, we're not the first to arrive at Jupiter. We're going to need to talk about what happens when you hit the keyhole. But first, you need to understand why the odds are so stacked against this being an accident. Part 3. Precision beyond probability. Why the 1 in 26,000 claim matters. Imagine you're standing in the middle of a football field. Someone hands you a dart and tells you to throw it randomly into the air. Somewhere in the city, miles away, there's a specific coin lying on a specific sidewalk. What are the odds your dart lands on that coin? Not in the neighbourhood, not on the block, on the coin. That's approximately the level of precision we're talking about when we discuss 3i Atlas and Jupiter's Hill sphere. The number that keeps getting thrown around is 1 in 26,000. That's the estimated probability that a random interstellar object would just happen to align itself with the narrow boundary of Jupiter's gravitational capture zone. 1 in 26,000. To understand why that number matters, you need to understand what it represents. It's not just about hitting a target in space. It's about hitting a target at the right time, with the right velocity, from the right angle. It's a 6-dimensional problem. When you describe an orbit, you're not just specifying a location, you're specifying position and velocity. 3 numbers for where you are, 3 numbers for where you're going. 6 dimensions. The keyhole around Jupiter isn't a circle drawn in space that exists everywhere at all times. It's a moving dynamic zone that only matters if you're approaching it at the correct speed and angle. Too fast, you blow right through. Too slow, you spiral in or fall back toward the sun. The margins are razor thin. Jupiter orbits the sun at about 13 kilometers per second. The Hill sphere radius is about 53.5 million kilometers when 3i Atlas arrives. but the keyhole itself, the region where you can actually slip into orbit without burning fuel, is much narrower. The difference between the calculated hill radius and the object's closest approach is about 60,000 kilometres. That's the margin. That's the window. In the scale of the solar system, it's microscopic. Now let's talk about the time dimension. Jupiter's hill sphere moves. The size fluctuates slightly as Jupiter follows its elliptical orbit around the Sun. The exact position of the sphere at any given moment depends on where Jupiter is relative to the Sun and the other planets. If 3i Atlas arrived a week earlier, or a week later, the keyhole would be in a different place. The alignment we're seeing isn't just spatial, it's temporal. The object is arriving at the right place at the right moment. Some orbital dynamicists argue that the 1 in 26,000 figure is exaggerated. They point out that as we refine our observations, uncertainties shrink, and what looked like a wildly improbable coincidence at first might turn out to be less improbable with better data. This is a fair point. Every time we get a new measurement, we update our models. The orbit we calculate today is more accurate than the orbit we calculated last month. Maybe the apparent precision is partly a product of that refinement process. But here's the counter-argument. Even if refinement makes the match less surprising, it doesn't explain the direction of the change. The non-gravitational acceleration didn't push 3i Atlas in a random direction. It pushed it toward the keyhole. If the acceleration had been in any other direction, the object would have missed Jupiter's hill sphere entirely. The fact that the push happened to be aligned with the exact vector needed to hit the target is where the improbability lives. Think of it this way. Imagine you're trying to hit a target in the dark. You fire a shot and miss. Then you fire again, but this time someone nudges your elbow mid-shot. The nudge could send your bullet anywhere, but instead the nudge corrects your aim, and you hit the bullseye. The odds of a random nudge improving your accuracy are much lower than the odds of the nudge sending you further off course. That's what we're seeing here. The course correction moved 3i Atlas closer to the target, not further away. There's also the issue of parameter space. Orbits exist in a 6-dimensional continuum. For any given starting point outside the solar system, there are effectively infinite trajectories an object could follow. Most of those trajectories don't bring you anywhere near the inner solar system. Of the tiny fraction that do, most don't pass near any planet. Of the vanishingly small fraction that pass near a planet, almost none pass through the planet's hill sphere. And of the absurdly rare fraction that do enter a hill sphere, virtually none enter at the exact boundary where capture is possible. The keyhole is a needle in a haystack inside a warehouse full of haystacks. Hitting it requires precision that doesn't happen by accident. And yet, 3i Atlas is about to hit it. In March of 2026, we'll know for sure. The object will either pass through the hill sphere boundary as predicted, or it won't. If it does, if the match holds, then we're left with two options. Option 1, we just witnessed the most spectacular coincidence in modern astronomy. Option 2, we witnessed something AIM. I want to be clear about something. Extraordinary claims require extraordinary evidence. The scientific method demands skepticism. We don't get to jump to conclusions just because a conclusion is exciting or terrifying. But we also don't get to dismiss patterns just because they make us uncomfortable. The data is what the data is. The numbers are what the numbers are. And right now, the numbers are screaming that something unusual is happening. Some critics argue that we're falling into a pattern-seeking trap. Humans are wired to find meaning in randomness. We see faces in clouds, conspiracies and coincidences. Maybe we're doing the same thing here. Maybe we're taking a natural phenomenon and draping it in narrative because the narrative is more interesting than the reality. That's possible. But it's also possible that sometimes the pattern is real. Sometimes the face in the cloud is an actual face. Sometimes the coincidence is a clue. The reason the 1 in 26,000 number matters isn't because it proves anything. It doesn't. What it does is shift the burden of proof. If the odds are truly that low, then the natural explanation becomes the extraordinary claim. Saying this is just a random rock that happened to perform a perfect intercept becomes harder to defend than saying this might be something else. At a certain point, invoking chance is more far-fetched than invoking intent. We'll circle back to the evidence question. But first, you need to understand why Jupiter matters. Because if this is intentional, if something is heading for Jupiter's hill sphere on purpose, then the question isn't just who sent it. The question is why Jupiter? And the answer to that question changes everything. Part 4. The Jupiter problem. Why the gas giant is the real prize. If you were an advanced civilization looking to establish a foothold in our solar system, where would you go? Earth seems like the obvious answer. It's where the life is, where the activity is, where the signals come from. But if you think strategically, if you think long-term, Earth is actually a terrible choice. Earth is loud, Earth is watched, Earth is crowded with sensors and satellites, and humans who ask uncomfortable questions. Earth is the worst place to set up shop if you want to go unnoticed. Jupiter, though. Jupiter is perfect. Let me walk you through why. First, there's the sheer gravitational dominance. Jupiter's mass is about 318 times Earth's. Its Hill sphere, that zone of gravitational influence we keep talking about, is enormous. At its widest, it extends over 50 million kilometres. Everything inside that bubble is effectively Jupiter's territory. The Sun's gravity is still there, still pulling, but Jupiter wins. If you release an object inside the Hill sphere with low enough velocity, it stays. It doesn't need engines. It doesn't need fuel. Gravity does the work. Second, there's the moon system. Jupiter has at least 79 confirmed moons, probably more we haven't found yet. Some of those moons are massive. Ganymede is bigger than Mercury. Europa might have a liquid ocean under its ice shell, an ocean with more water than all of Earth's oceans combined. Io is the most volcanically active body in the solar system, constantly resurfacing itself with fresh lava. These aren't just rocks, these are worlds, and they orbit in a complex, stable system that's been running for billions of years. If you wanted infrastructure, if you wanted resources, if you wanted places to hide, Jupiter's moons are a gold mine. Third, there's the magnetosphere. Jupiter's magnetic field is the strongest of any planet in the solar system, about 20,000 times stronger than Earth's. It stretches for millions of kilometers in every direction, trapping charged particles, generating intense radiation belts. For humans, that radiation is deadly. For machines, for probes designed to operate in harsh environments, it's a non-issue, and the magnetosphere itself could be useful. It's a natural accelerator, it's a particle detector, it's an energy source if you know how to tap it. An advanced civilization could do a lot with a magnetic field that powerful. Fourth, there's the strategic position. Jupiter sits at the boundary between the inner and outer solar system. From Jupiter, you can see everything. You can monitor the asteroid belt. You can watch Mars. You can track Earth. You have a commanding view of the inner planets while remaining far enough out that nobody's paying close attention. It's the high ground. In military terms, controlling the high ground wins wars. In cosmic terms, controlling Jupiter wins the solar system. Now let's talk about the Hill sphere boundary specifically. Why would you aim for the edge instead of diving straight into Jupiter's orbit? Because the edge is where the math works in your favour. At the boundary of the Hill sphere, Jupiter's gravitational influence is strong enough to hold on to objects, but the escape velocity is relatively low. Avi Loeb calculated that at a distance of 53.5 million kilometres from Jupiter, the escape velocity is about 2.2 kilometres per second. That's nothing. That's walking speed on a cosmic scale. What that means is, if you arrive at the edge of the Hill sphere and you want to drop off probes, you barely need to slow them down. A tiny nudge, a tiny burn, and they're in orbit. They don't fall back into interstellar space, they don't crash into Jupiter, they just drift, held in place by the planet's gravity, waiting, watching. And here's the terrifying part. Once you're in orbit around Jupiter, once you're tucked into the Hill sphere, you're almost impossible to detect from Earth. We have a hard enough time finding asteroids in our own neighbourhood. Finding small objects in the chaos of Jupiter's orbital space, amid all the moons and Trojan asteroids and dust, is like finding a needle in a needle factory. Unless something gives off a signal, unless it reflects enough light to show up on our telescopes, it's invisible. This is why some researchers are calling 3i Atlas a mothership. The term sounds dramatic, but it's descriptive. A mothership doesn't stay, it delivers. It carries a payload across vast distances and deposits that payload at a strategic location. Then it either leaves or parks somewhere quiet. The payload, the probes, they're the ones that do the work. They're the ones that watch, that listen, that gather data. The mothership is just the delivery system. If that's what's happening here, if 3i Atlas drops off a cluster of small probes at Jupiter's Hill sphere, we might never see them. Not unless we're looking very carefully. Not unless we know what to look for. And even then, they'd be nearly indistinguishable from natural debris. A probe the size of a car would look like a tiny moon. A probe the size of a person would be invisible. You might be wondering, if Jupiter is so strategic, why haven't we seen evidence of other visitors? Why aren't there already signs of probes or infrastructure around Jupiter? The answer is, maybe there are. We've only been seriously studying Jupiter for a few decades. Juno arrived in 2016. Before that, we had Galileo, which orbited from 1995 to 2003. Before that, we had flybys, quick looks, snapshots. We've barely scratched the surface of cataloguing Jupiter's environment. There could be dozens of small objects in unusual orbits that we've written off as captured asteroids or debris from moon collisions. We don't know what we're looking for, so we don't see it. But if 3i Atlas arrives in March of 2026 and something changes, if new objects appear, if orbits shift, if there's any indication that the Jovian system just got more crowded, then we'll have our answer. We'll know that Earth wasn't the target. We were never the target. We were just the neighbours. Jupiter was always the prize. And if someone already claimed it, if something is already there waiting, then the question becomes, what do they want with us? Are we being studied? Are we being ignored? Or are we part of a plan we don't understand yet? The clock is ticking. March 2026 is coming, and when it arrives, we'll find out if Jupiter's hill sphere is empty or occupied. Part 5. What Juno will see. The 2026 surveillance window. There's a spacecraft already at Jupiter. Right now, as you're reading this, NASA's Juno probe is carving elliptical orbits around the gas giant, swooping close to the cloud tops and then swinging out into the radiation belts. Juno launched in 2011 and arrived at Jupiter in July of 2016. Its mission is to study Jupiter's composition, gravity field, magnetic field, and polar magnetosphere. It's been sending back stunning images of the planet's swirling storms, its auroras, its mysterious interior. But in March of 2026, Juno might witness something it wasn't designed to see. Something that changes its mission profile entirely. Juno's orbit is highly elliptical. At its closest approach, called perigove, it skims just a few thousand kilometres above Jupiter's clouds. At its farthest point, apogee, it swings out to several million kilometres. The orbit takes about 53 days to complete. That means roughly every 2 months Juno gets a close-up view of Jupiter, and the rest of the time it's coasting through the outer magnetosphere. The spacecraft is equipped with a suite of instruments: JunoCam, which captures visible light images; GIRUM, the infrared mapper; the WAVES instrument, which detects radio and plasma waves; magnetometers; particle detectors; gravity sensors. None of these instruments were designed to look for artificial objects. Juno's mission is planetary science, not SETI. But the instruments are sensitive. If something unusual appears in Jupiter's vicinity, if there's a sudden glint of reflected sunlight, an unexpected radio signal, a gravitational anomaly, Juno could pick it up. Whether anyone notices depends on whether anyone is paying attention. Here's what we might see if the mothership hypothesis is correct. Scenario 1. 3i Atlas passes through the hill sphere boundary in mid-March 2026 and releases a cluster of smaller objects. These objects, let's call them probes, use minimal propulsion to enter stable orbits around Jupiter. They're small, maybe a few meters across, designed to be low profile. From Earth, they'd be nearly impossible to detect, but Juno, if it happens to be in the right part of its orbit at the right time, might catch a reflection. A brief flash of light, a transient signal, something that shows up for a few frames and then disappears. Scenario 2. The probes don't reflect light. They're coated in something that absorbs rather than reflects. Stealth technology. But they emit heat. Everything warmer than absolute zero emits infrared radiation. GIRUM, Juno's infrared instrument, could detect a cluster of warm objects against the cold background of space. Again, this depends on timing and luck. If Juno is looking in the wrong direction, or if the probes are too faint, we miss it. Scenario 3. The probes use some form of active propulsion or communication. Maybe they talk to each other. Maybe they send signals back toward 3i Atlas or out into interstellar space. The WAVES instrument could pick up radio emissions, unusual frequencies, modulated signals. Anything that doesn't match the natural radio noise from Jupiter's magnetosphere would stand out. This is the scenario where detection becomes almost certain. but it's also the scenario where the probes would need to be either careless or willing to be seen. Scenario 4, nothing happens. 3i Atlas passes through the Hill sphere, exits on the other side and continues into the outer solar system. No probes, no deployment. It was just a rock after all, and the whole mothership hypothesis collapses. This is the scenario that most scientists expect. It's the null hypothesis. But if this is what happens, it raises its own questions. Why did the object perform such a precise maneuver? Why did it aim for the keyhole if it wasn't planning to use it? The problem with all of these scenarios is that we're operating blind. Juno isn't designed to be a watchdog. It's focused on Jupiter, not on the space around Jupiter. Its instruments have limited fields of view. Its orbit is fixed. If something happens outside its line of sight, if the timing is off by a few hours, we miss it. And even if Juno does capture something, the data takes time to transmit. The spacecraft is nearly 800 million kilometers from Earth. Signals travel at the speed of light, which means there's a delay of about 40 minutes each way. We won't know what Juno sees until well after it sees it. There's also the question of what NASA does with the data. If Juno detects something anomalous, does it get flagged immediately? Does someone in mission control notice and escalate? Or does it sit in a data queue for weeks, while scientists process the routine observations first? Space missions generate enormous amounts of data. Most of it is mundane. Sorting through it, looking for the one unexpected thing, is like panning for gold. You need to know what you're looking for, and right now, most of the people analysing Juno data are looking for storms and magnetic field lines, not probes. But let's assume the best-case scenario. Let's assume someone is watching. Let's assume that between now and March, enough people become aware of the 3i Atlas predictions that when the object arrives, we're ready. Telescopes are pointed, Juno's operations are adjusted, we're actually looking for something. What then? If we detect even one object that can't be explained naturally, if we find something in orbit around Jupiter that shouldn't be there, the implications are immediate. It means we're not alone. It means someone else has technology capable of interstellar travel and orbital deployment. It means Earth is no longer the only game in town, and we're probably not the most advanced players. It means the solar system is already claimed, at least partially, and it means we need to figure out what comes next. Do we try to communicate? Do we observe from a distance? Do we prepare for possibilities we've only ever seen in fiction? On the other hand, if we detect nothing, if Juno sees no evidence of deployment, we're left with uncertainty. Did nothing happen, or did something happen that we missed? Did the probes deploy but remain invisible? Did 3i Atlas change its mind? Or was the whole thing a misunderstanding, a case of scientists seeing patterns where none exist? March 2026 is the deadline. The surveillance window is narrow. If something is going to happen, it's going to happen then. And when it does, Juno will be the first witness. Whether we believe what it sees is another question. Entirely. The pieces are in place. The object is approaching. The instruments are active. All we can do now is wait and watch. But while we wait, there are deeper questions we need to ask. Questions about why this object exists in the first place. Questions about what it might be, how it might work, and what its existence says about the universe we thought we understood. Let's talk about the mothership. Part 6. The Mothership Hypothesis. Design Logic. Behind a slow-drift interstellar vessel, imagine you need to send something across the galaxy. Not a signal, something physical. A probe, a machine, maybe several. Your destination is a star system you've identified as interesting. Maybe it has planets, maybe it has life. You want to know what's there, but you can't go yourself. The distances are too vast, the timescale's too long, so you build something that can make the trip. What does that something look like? First, forget everything you've seen in movies. No warp drives, no hyperspace, just physics. Brutal, unforgiving physics. The speed of light is an iron law. You're not breaking it. That means your travel time is measured in years at best, millennia more likely. If your destination is 10 light years away and you're travelling at 1% of light speed, which is already absurdly fast, the trip takes 1,000 years. You need a vessel that can survive 1,000 years in the void. No repairs, no resupply, just endurance. Second, energy. Moving mass takes energy, a lot of it. The faster you want to go, the more energy you need. There's no friction in space, so once you're up to speed you coast. but getting to speed in the first place is expensive. You can't carry fuel the way a rocket does. The fuel itself has mass, which means you need more fuel to accelerate the fuel, which adds more mass, which needs more fuel. It's a death spiral. So you use something else. Solar sails maybe, magnetic sails, beamed propulsion from your home system, gravity assists, anything that doesn't require you to carry your energy source. Third, detection. If you're travelling through someone else's solar system, you probably don't want to announce yourself. Maybe you're peaceful, but maybe the locals aren't. Maybe you want to observe without interfering. Either way, stealth is valuable, so you make your vessel look like something natural. You give it the albedo of a comet. You let it tumble like a rock. You don't emit signals. You don't reflect more light than you have to. You drift quietly, just another piece of interstellar debris. Now let's apply this logic to 3i Atlas. What if it's not a comet? What if it's a vessel designed to look like a comet? The engineering makes sense. You coat the outside in ice and carbon. You let it accumulate dust during the long journey. By the time it arrives, it's indistinguishable from a natural object. When it gets close to the sun, the ice heats up and outgasses just like a comet would. Perfect camouflage. But underneath, there's structure, machinery, instruments, a payload. The non-gravitational acceleration we detected could be outgassing, or it could be propulsion masquerading as outgassing. If you time your burn to coincide with perihelion, when natural comets are most active, nobody suspects. The jets we see could be exhaust or they could be venting. The difference is hard to prove without close-up inspection. And who's going to send a spacecraft to inspect a random comet from outside the solar system? We barely have the budget for missions to our own comets. The trajectory is the giveaway. A natural comet doesn't aim for the edge of Jupiter's hill sphere. It doesn't execute a precision maneuver while hidden behind the sun, but a mothership does. Because the hill sphere is where you deploy your payload. You arrive at the boundary with minimal velocity. You release your probes. They each make a tiny burn, just enough to enter stable orbits. Then the mothership either continues on its way, exits the solar system, or parks in a distant orbit where it's unlikely to be noticed. The probes are the real mission. They're small, efficient, autonomous. They don't need life support. They don't need to go home. They're designed to operate for decades, maybe centuries. They watch, they listen, they collect data. Maybe they communicate with each other. Maybe they relay information back to the mothership, which relays it further into space. Or maybe they just store everything locally, waiting for a retrieval mission that may never come. Now let's talk about propulsion options. If you're building an interstellar mothership, what technologies are actually feasible? Rocket engines are out. Chemical propulsion is laughable at these scales. Ion drives are better, but still require massive amounts of fuel for a journey measured in light years, so you look at alternatives. Magnetic sails use the interstellar medium itself as reaction mass. You deploy a massive magnetic field that interacts with charged particles in space, giving you thrust without fuel. It's slow, but you have time. Solar sails use photon pressure from stars. As you approach a new system, you can use that system's star to decelerate. Clever engineering turns your approach into a braking maneuver. There's also the possibility of beamed propulsion. Your home civilization fires a laser or particle beam at your sail. You ride that beam outward, accelerating continuously until you're beyond range. Then you coast for centuries. When you approach your destination, you flip the sail and use the target star's light to slow down. No fuel needed, just time and patience, and a sail that can survive the journey. The measured acceleration of 3i Atlas, about 5 times 10 to the negative 7th astronomical units per day squared, fits within the range of these technologies. It's small enough to be subtle, large enough to matter over time. If you applied that acceleration constantly for a year, you'd change your velocity by about 60 meters per second. That's not much, but applied at perihelion, when you're already moving at 40 kilometers per second relative to the sun, it's enough to shift your trajectory by millions of kilometers downstream. The Oberth effect multiplies your effort. But here's where the model gets uncomfortable. If 3i Atlas is a mothership, it's been travelling for a very long time. Interstellar space is vast. Even the nearest stars are light years away. If this object came from Proxima Centauri, the closest star system, and travelled at a reasonable cruise speed of 1% of light speed, the journey took over 400 years. If it came from further away, we're talking thousands of years, maybe longer. That raises questions about whoever built it. Are they still around? Did they launch this thing and then go extinct? Or are they out there now, waiting for data? And if they're waiting, what do they do when 3i Atlas completes its mission? Do they send another? Do they come themselves? Or do they just file the report and move on to the next star? The other possibility, and this is where things get really speculative, is that 3i Atlas isn't the only one. Maybe there are dozens of these motherships, each targeting a different planet in our solar system. Maybe Earth already has visitors in orbit that we mistook for asteroids. Maybe Mars does, maybe Venus. We've only been looking carefully for a few decades. We've only had the technology to detect small, dark objects for a fraction of that time. How many could we have missed? Critics of the mothership hypothesis point out that we have no direct evidence of artificial structure, no metals, no geometric shapes, no signals. Everything we've observed about 3i Atlas can be explained, at least in theory, by natural processes. And they're right, we don't have proof. What we have is a pattern that fits the hypothesis uncomfortably well. But patterns aren't proof. Proof requires close examination, spectroscopy, imaging, maybe even a flyby mission, and we're not going to get that. 3i Atlas is moving too fast, and we didn't have enough warning to launch an intercept mission. So we're left with inference, with probabilities, with the uncomfortable question of whether Occam's razor applies. Is the simplest explanation really that this is a natural object that just happened to execute a perfect maneuver? Or is the simplest explanation that something aimed it? In science, we're trained to prefer natural explanations. But natural and simple aren't always the same thing. Sometimes the natural explanation requires more coincidences than the artificial one. There's also the engineering perspective. If you were designing an interstellar probe mission, this is exactly how you'd do it. You'd aim for the outer planets. You'd use their gravity wells as deployment zones. You'd disguise your vessels as natural objects. You'd time your maneuvers to minimize detection. Every choice 3i Atlas has made, every aspect of its behavior, aligns with what a competent engineer would design. That doesn't prove intent, but it's hard to ignore. The final piece of the mothership hypothesis is the why. Why would anyone send probes to our solar system? What's here that's worth a 1,000-year journey? The obvious answer is life. Earth is the only planet we know of with a biosphere. From a distance, even from light years away, you could detect oxygen in our atmosphere. You could see the chemical disequilibrium that screams biology. If you're searching for life, Earth is a beacon. And if you want to study that life without interfering, Jupiter is where you set up shop. But maybe it's not about life. Maybe it's about resources. The asteroid belt, Jupiter's moons, the Kuiper belt. Our solar system is rich in materials. If you're a spacefaring civilization looking for raw materials, why mine your own planets when you can harvest from systems that can't defend themselves? We're barely capable of reaching our own moon. We're no threat to anyone with interstellar capability. Or maybe it's strategic. Maybe our solar system is along a route between two other destinations. Maybe Jupiter is a convenient way station. Maybe we're being catalogued, our system added to a database of stellar neighbourhoods. Maybe we're not important at all, we're just here and someone took note. The truth is, we don't know. We can't know without more data. And that's what makes March 2026 so critical. If the mothership hypothesis is correct, if probes are deployed, we'll see evidence. Maybe not immediately, maybe not conclusively, but we'll see something. And that something will force us to ask bigger questions. Questions about who's out there. Questions about what they want. Questions about whether we're ready for the answer. But before we get there, we need to talk about timing. Because the fact that this is happening now, in 2026, might not be random either. Part 7. The timing paradox. Why 20? 26 matters beyond astronomy. Most comet stories end at perihelion. The object reaches its closest point to the sun, puts on a show, maybe develops a tail, and then fades back into obscurity. We take our measurements, update our models, and move on. But with 3i Atlas, perihelion was just the beginning. The real event, the real moment of truth comes months later, in March of 2026. And the more you think about that timing, the stranger it gets. Let's start with what's happening in March. 3i Atlas will pass through the edge of Jupiter's hill sphere. We've covered that. But there's a broader context. Jupiter itself goes through cycles. Its magnetosphere fluctuates. Its radiation belts wax and wane. The planet's axial tilt creates seasonal variations in how it interacts with the solar wind. If you, were planning to deploy probes into the Jovian environment, you'd want to time it right. You'd want to arrive when conditions are favourable, when the radiation is manageable, when the magnetosphere is in a particular state. Now, we don't know if March 2026 corresponds to any special alignment in Jupiter's cycles. The data isn't public yet, but it's worth noting that Jupiter's magnetosphere is one of the most complex environments in the solar system. It's like a miniature solar system unto itself. Plasma flows, magnetic field lines, particle acceleration. If you're dropping off sensitive equipment, you'd want to choose your window carefully. There's also the question of solar activity. The Sun goes through an 11-year cycle of activity from solar minimum to solar maximum and back. During solar maximum, the Sun produces more flares, more coronal mass ejections, more radiation. During solar minimum, it's quieter. These cycles affect the entire solar system. They affect the density of the interstellar medium around us. They affect how the heliosphere, the bubble of solar wind, interacts with interstellar space. If you're entering the solar system from outside, you'd feel these effects. 2025 and 2026 fall near a solar maximum. The Sun is more active than it's been in years. That might seem like a bad time to deploy sensitive equipment. More radiation means more risk. But it could also be a good time if you're trying to hide. More solar activity means more noise, more interference, more natural radio emissions. If you're trying to slip something into orbit without being detected, doing it when the background is loud makes sense. Your signal gets lost in the chaos. Then there's the heliosphere itself. Recent observations, some of which we'll talk about later, show that the boundary of the heliosphere is changing. It's shrinking. It's becoming asymmetrical. The shape and size of the heliosphere determine how interstellar objects enter the solar system. They determine how much drag you feel from the interstellar medium. They determine whether your trajectory bends or stays straight. If you're navigating from outside, you'd need to account for these factors. Maybe 3i Atlas chose this moment because the heliosphere is in a particular configuration, a configuration that makes the Jupiter intercept easier. But let's zoom out even further. Let's talk about what humans are doing in 2026. We're in the middle of a space renaissance. Commercial spaceflight is taking off. NASA's Artemis program is planning lunar missions. SpaceX is building Starship for Mars. China is establishing a lunar base. Multiple countries are launching deep space probes. Compared to 20 years ago, we're far more active. We're far more capable. We're making noise. If you're an outside observer, if you've been watching us for a while, you'd notice this uptick. You'd see that humanity is transitioning from a single planet, species, to a spacefaring one. This is a critical moment in our development. It's the moment when we stop being a curiosity and start being a potential factor. If you wanted to assess our capabilities, to see what we're capable of, now would be the time. Before we spread out, before we become harder to track, there's a darker implication here too. If the timing isn't random, if 3i Atlas is arriving now because we're becoming more active, then the deployment might not be about passive observation. It might be about preparation. Preparation for what? Intervention? Communication? Containment? We don't know. But the fact that the arrival coincides with our own space expansion is uncomfortable. Or maybe I'm reading too much into it. Maybe the timing is just orbital mechanics. 3i Atlas left its origin point however many thousands of years ago. It's been coasting ever since. The fact that it's arriving now, during our space age, is pure coincidence. The universe doesn't care about our timelines. Comets don't schedule their arrivals around human history. But if this isn't a comet, if it's something else, then the timing might be deliberate. And deliberate timing implies awareness, implies monitoring, implies someone has been watching us long enough to know when to arrive. There's another angle to consider. Cosmic ray background. The solar system moves through the galaxy, and as it does, we pass through regions of varying cosmic ray density. These rays affect everything from cloud formation on Earth to mutation rates in DNA. Some scientists have speculated that cosmic ray fluctuations correlate with mass extinction events, though the evidence is contentious. The point is, the radiation environment changes over time. If you're deploying probes that need to operate in a specific radiation regime, you'd time your arrival accordingly. Jupiter's position in its orbit matters too. The planet takes about 12 Earth years to orbit the Sun. In March 2026, Jupiter will be in a specific part of its orbit. Maybe that position matters. Maybe it's closer to certain asteroid populations. Maybe the angle relative to the inner planets makes communication easier. Maybe it's nothing. But when you're dealing with precision maneuvers, every detail could be significant. Here's what keeps me up at night. If the timing is deliberate, it means someone has been planning this for a very long time. Interstellar travel takes centuries at minimum. Whoever launched 3i Atlas did so long before humans discovered electricity, long before we had telescopes, maybe even before recorded history. They aimed it at our solar system knowing that by the time it arrived, we'd be here. They couldn't have known exactly what we'd be capable of, but they knew we'd exist. That level of foresight is staggering, and it suggests a patience that's almost incomprehensible. The alternative is that the timing is coincidence. 3i Atlas is natural. It wandered into our system at random. The precision maneuver is a misinterpretation of natural outgassing. The Hill-sphere alignment is luck. The arrival during our space age is chance. All of it, just chance. And you know what? Maybe it is. Coincidences happen. The universe is big. Unlikely things occur. But the more coincidences stack up, the harder they are to swallow. Between now and March, we need to be watching. Not just Jupiter, not just 3i Atlas. Everything. The Sun's activity, the heliosphere, Jupiter's magnetosphere, Earth's own space infrastructure. If something is about to happen, if this moment is as significant as it seems, we'll see ripples, anomalies, patterns, maybe subtle, maybe obvious, but they'll be there. And if we're really unlucky, we'll see more than ripples. We'll see action. Because if Jupiter is the high ground, if it's the strategic prize, then whoever claims it first has an enormous advantage, and we're not even close to claiming it. Part 8. The High Ground Strategy. How Jupiter enables system-wide domination. There's a concept in military strategy called control the high ground. If you're fighting on a hill, you want to be at the top. The person at the top sees everything. They can roll rocks down on attackers. They dictate the terms of engagement. In terrestrial warfare, height is power. In space, the high ground isn't about altitude, it's about gravity wells. And in our solar system, Jupiter is the ultimate high ground. Let me explain why this matters. Jupiter's mass is about 2.5 times the combined mass of all the other planets. When you have that much mass, you dominate your orbital neighbourhood. Everything near you feels your pull. Asteroids get captured. Comets get deflected. Your Hill sphere extends tens of millions of kilometres. You're not just a planet, you're a gravitational fortress. If you wanted to control the solar system, you wouldn't start with Earth. Earth is too small, too weak gravitationally. You'd start with Jupiter. Because from Jupiter you can reach anywhere. The planet's gravity well is a catapult. You can use it to sling probes toward the inner planets, toward the outer planets, toward the Kuiper belt. Minimal fuel required, just timing and trajectory. Jupiter is the hub. Everything else is a spoke. Now let's talk infrastructure. Jupiter has at least 79 moons. 4 of them, the Galilean moons, are massive. Io is the most volcanically active body we know of. Constant resurfacing, extreme heat, a harsh environment, but rich in sulfur and other materials. Europa has a subsurface ocean, liquid water under kilometres of ice, possibly more water than all of Earth's oceans. Ganymede is the largest moon in the solar system. It has its own magnetic field. Callisto is ancient, heavily cratered, stable. Each of these moons is a potential base, a potential resource depot, a potential factory. If you're an advanced civilization with the technology to harvest resources in situ, Jupiter's moons are a jackpot. You don't need to bring materials with you across interstellar space. You mine them locally. You build infrastructure using what's there. Europa's water becomes fuel, hydrogen and oxygen, perfect for chemical rockets or for sustaining biological processes. Io's sulfur becomes industrial feedstock. Ganymede's metals become construction material. You bootstrap an entire industrial complex without ever touching Earth. Then there's the magnetosphere. Jupiter's magnetic field is a monster. It traps charged particles, creating radiation belts that would kill an unshielded human in hours. But those same radiation belts are an energy source. If you know how to tap them, you have a nearly limitless supply of high-energy particles. You can use them to power your equipment. You can use them to communicate. You can use them as a weapon if you need to. The magnetosphere itself acts as a natural particle accelerator. Physics experiments that require massive machines on Earth happen naturally in Jupiter's environment. From a surveillance perspective, Jupiter is ideal. You're far enough from the sun that solar glare isn't an issue. You have a stable platform. Your line of sight covers the entire inner solar system. You can track ships, monitor communications, watch for technological development, and nobody on Earth is looking back at you with the same level of scrutiny. We point our telescopes outward, toward distant galaxies. We rarely study our own backyard in detail. There's also the Trojan asteroids. Jupiter has two huge swarms of asteroids that share its orbit, one ahead of the planet and one behind. These Trojans are stable. They've been there for billions of years. They're dark, hard to see, perfect for hiding. If you wanted to place sensors or equipment where they'd never be noticed, the Trojans are ideal. There are thousands of them. We've catalogued maybe a few hundred in any detail. The rest are just dots on a map. Any one of them could be artificial, and we'd never know. Now let's talk strategy. Imagine you're a spacefaring civilization. You've identified Earth as a planet with life. Maybe you're interested in studying that life. Maybe you're interested in the planet's resources. Maybe you just want to keep an eye on us in case we become a threat. You don't want to land. Too risky. Too disruptive. Instead, you set up a sensor network. Where do you put it? You put it at Jupiter. You deploy a cluster of small autonomous probes in the Hill sphere. Each probe is smart enough to maintain its own orbit. They communicate with each other, forming a mesh network. They watch the inner planets. They relay data back to a central node, maybe the mothership, maybe something else, and they wait. For decades. For centuries. They're patient because they're machines. They don't care how long it takes. From Earth's perspective, we'd never see them. The probes are small, they don't emit light. They're in the noise of Jupiter's environment. We'd need to be actively looking, with high-resolution instruments, and even then we'd probably miss them. It's the perfect surveillance setup. Passive, persistent, invisible. But it's not just about watching. It's about access. If you control Jupiter, you control the outer solar system. You can intercept objects coming from the Kuiper belt. You can monitor traffic heading to the asteroid belt. You become the gatekeeper. Any human mission to the outer planets has to pass through your domain. You see them coming long before they see you. And if things turn hostile, if for some reason you need to take action, Jupiter gives you options. You can drop rocks, redirect asteroids, use the magnetosphere as a weapon. You have the high ground, and high ground wins. The terrifying part is that this strategy is so obvious, any advanced civilization would think of it. Which means if interstellar visitors exist, if they've been here before, Jupiter is where they'd be. And if they're there now, we're late to the game. They've already claimed the territory, we're just tenants in our own solar system, and we don't even know it. There's a counter-argument, of course. If someone controls Jupiter, why haven't they contacted us? Why haven't they made themselves known? Maybe because they don't need to. Maybe because we're not a threat. Maybe because they're following some kind of non-interference protocol. Or maybe they have contacted us and we didn't recognize the message. Maybe the signal is there, in the data, and we just haven't decoded it yet. Or maybe nobody's there. Maybe Jupiter is empty. Maybe we're alone, and all of this speculation is just humans projecting strategy onto nature. That's possible, but it's also possible that we're about to find out. Because if 3i Atlas deploys probes in March, if something changes in the Jovian environment, we'll have our answer. The high ground will be occupied, and we'll need to decide what to do about it. Before we get to that decision, though, we need to talk about what the agencies aren't saying, because there's a gap between what we know and what's being disclosed, and that gap is growing. Part 9, Conspiracies and Counter-Conspiracies, What Agencies Aren't Saying. Let's talk about silence, not the absence of sound, but the absence of information. In the age of instant communication, when scientific data is supposed to be open and transparent, there are gaps, periods where observations should exist but don't, images that should have been released but weren't, and those gaps, intentional or not, feed speculation. With 3i Atlas, there's a window of about 45 days during solar conjunction when publicly available imagery goes dark. The object was there. We know it was there because we detected it before and after. But during that critical period, when it was closest to the Sun, when the alleged maneuver occurred, we have almost nothing. A handful of data points, sparse astrometric measurements, and then silence. Now, there are legitimate reasons for this. Observing an object near the Sun is difficult. Ground-based telescopes can't do it. You'd burn out your sensors. Space-based observatories like SOHO or Stereo have coronagraphs that block the Sun's light. but their fields of view are limited. If 3i Atlas didn't pass directly through those fields, we wouldn't see it. It's entirely possible that the gap is just bad luck, bad geometry, wrong place, wrong time. But it's also possible that observations exist and haven't been released. Space agencies don't publish everything immediately. Data goes through processing, calibration, analysis. Sometimes it sits in a queue for months before anyone looks at it. Sometimes it's classified, especially if military satellites were involved. The line between scientific observation and national security is blurry when it comes to space. If something unusual was detected, if there was any indication that 3i Atlas isn't natural, that information might not be public yet, then there are the fringe claims. And I want to be clear, these are unverified, they're rumours. Speculation posted on forums, amplified by tabloids, impossible to confirm, but they're out there, and people are talking about them, so let's address them. One claim is that metal alloys were detected in spectroscopic analysis of 3i Atlas. Alloys that don't occur naturally. Combinations of elements that require industrial processes. The New York Post ran a story about this, citing unnamed sources. Mainstream scientists immediately pushed back, saying there's no credible evidence for artificial materials, but the rumour persists. Another claim is that Juno has already detected anomalous objects near Jupiter. Small, fast-moving targets that don't match any known moons or asteroids. Again, no official confirmation. NASA's public statements say everything Juno has seen is consistent with natural phenomena. But people point to gaps in the data releases, periods where Juno's images aren't published on schedule, and they ask why. What's being held back? There's also the question of international cooperation, or lack thereof. Multiple countries have space agencies. Multiple observatories around the world were tracking 3i Atlas. But there's no unified database, no central repository where all the observations are compiled in real time. Different teams use different models. They release data on different schedules. Sometimes the handoffs between observatories introduce delays. Sometimes data gets lost in translation. Is that suspicious? Or is it just bureaucratic inefficiency? Let's play devil's advocate for a moment. Suppose something unusual was detected. Suppose there's evidence that 3i Atlas is artificial. What would the agencies do? Would they announce it immediately? Or would they wait? Wait for confirmation? Wait for peer review? Wait until they have a plan for how to communicate it? You don't want to cause a panic, you don't want to be wrong. So you sit on the data, you analyse it privately, you consult with colleagues behind closed doors, and while you're doing that, the silence grows. From the outside, that silence looks like a cover-up. People start connecting dots that may not be connected. They point to classified military satellite programs. They mention rumours of secret space surveillance networks. They ask why certain astronomers suddenly stop talking about 3i Atlas. And before you know it, you have a conspiracy theory, fed by secrecy, fed by ambiguity, fed by the very real possibility that something is being withheld. The counter-conspiracy view is simpler. The agencies are being totally open. The gaps in data are mundane. Technical issues, observational challenges, limited resources. Scientists are busy. They're working on a dozen projects at once. 3i Atlas is interesting, but it's one object among thousands they're tracking. The delay in publishing isn't nefarious. It's normal. And the lack of evidence for anything artificial is because there's nothing artificial to find. This view is probably correct. Most conspiracy theories are wrong. Most gaps have boring explanations. The problem is sometimes conspiracies are real. Sometimes information is withheld. Sometimes the boring explanation is cover for something else. And without transparency, without access to the raw data, we can't tell the difference. Here's what we know for sure. 3i Atlas is behaving in ways that are difficult to explain naturally. The trajectory, the timing, the precision. These are facts. The interpretations vary, but the observations are solid. We also know that agencies have resources we don't. Classified telescopes, military satellites, data streams that never go public. If there's more to the story, they'd see it first. And if they saw it, we might not hear about it for months, maybe years. There's an analytic framework we can use here. When evaluating any claim, ask 3 questions. First, what's the source? Is it credible? Are they an expert? Do they have access to the data? Second, what's the evidence? Is it verifiable? Can it be independently confirmed? Third, what's the motivation? Why would someone release this information? Why would someone withhold it? Apply that framework to the 3i Atlas claims, and most of them fall apart. But not all of them. The claim that 3i Atlas performed a precision maneuver comes from Avi Loeb, a respected astronomer at Harvard. The data comes from JPL Horizons, a public database. The calculations can be checked. That claim has weight. The claim that metal alloys were detected comes from an unnamed source in a tabloid. No peer review, no verification. That claim is weak. The claim that Juno detected something comes from internet forums. No data, no images. That claim is noise. But here's the thing. The absence of evidence isn't evidence of absence. Just because we don't have a clear image of a probe doesn't mean there isn't a probe. Just because NASA hasn't announced anything doesn't mean there's nothing to announce. We're limited by what we can see, what we can measure, what gets shared. And those limits leave room for doubt, so where does that leave us? In March 2026 we'll get more data. Juno will be watching. Earth-based telescopes will be pointed at Jupiter. If something is there, if probes are deployed, we'll see evidence. Maybe direct, maybe circumstantial, but we'll see something. And if we don't, if the Hill sphere remains empty, then the mothership hypothesis dies. 3i Atlas was just a comet. An unusually precise comet, but a comet nonetheless. Until then, we wait, we watch, and we ask questions. Because transparency matters. Because the difference between a cover-up and a cautious delay is hard to spot from the outside. And because if there is something to this story, if we're on the verge of confirming that we're not alone, then we deserve to know. Not months later, not years later. Now. But before we get too focused on 3i Atlas, we should zoom out. Because this object isn't the only interstellar visitor we've seen, and the pattern, if there is one, might be bigger than we think. Part 10. The Big Picture. Other interstellar oddities that suddenly look different. 3i Atlas isn't the first, it's the third. Or at least it's the third we've detected. And when you line them up, when you look at them together, something shifts. Patterns emerge. Questions multiply. Let's start from the beginning. October 2017. A telescope in Hawaii picks up something strange. A faint object moving fast. Too fast. The trajectory is hyperbolic, meaning it's not bound to the sun. It came from outside. It's just passing through. They name it One-Eye Oumuamua, Hawaiian for scout or messenger. The shape is bizarre. Long, thin, tumbling end over end. Initial estimates suggest it's about 400 metres long and only 40 metres wide. A cigar. A needle. Nothing like any asteroid or comet we've seen before. Then the behaviour gets weirder. As Oumuamua leaves the solar system, it accelerates. Not much, just a tiny push. But it's there. Non-gravitational acceleration, just like with 3i Atlas. Scientists scramble to explain it. Outgassing is the natural answer. But there's no visible coma, no tail, no evidence of gas escaping. Some suggest it's a nitrogen iceberg, outgassing nitrogen that we can't easily see. Others point to the shape, arguing that even a small amount of outgassing from such an elongated object would produce observable rotation changes, which we don't see. Avi Loeb, the same astronomer now analysing 3i Atlas, suggests that Oumuamua might be artificial. Maybe a light sail, a thin reflective sheet pushed by starlight. The shape fits, the acceleration fits, the lack of outgassing fits. Mainstream scientists push back hard. Too speculative, they say. Not enough evidence. Loeb stands by his analysis. The debate rages for years, and then we move on. Oumuamua leaves the solar system. We lose track of it. End of story. Or not. Because in August 2019 we get visitor number 2. 2i Borisov. This one looks more like a comet. It has a coma. It outgasses. Spectroscopy shows water vapour, carbon monoxide, the usual comet stuff. Scientists breathe a sigh of relief. See? Interstellar objects can be normal. Borisov is proof. It's just a comet from another star system. Nothing mysterious. But even Borisov has oddities. Its composition is slightly off. The ratio of carbon to oxygen is higher than we expect. The dust-to-gas ratio is unusual. It's close to what we see in our comets, but not quite. And its nucleus, the solid core, seems to be fragmenting as it passes the sun. Why? We don't know. Maybe it's been in interstellar space so long that it's structurally weak. Maybe the thermal stress breaks it apart. Or maybe there's something else going on. Now we have 3i Atlas, detected in 2025. Unlike Oumuamua, It's big, several kilometers across. Unlike Borisov, its behavior is precise, targeted. The non-gravitational acceleration isn't random. It shifts the trajectory toward a specific destination. The more we study it, the less it looks like a comet. Or rather, it looks like a comet that's trying very hard to look like a comet. So let's ask the uncomfortable question. What if they're all related? What if Oumuamua, Borisov and 3I Atlas are part of a pattern? Not random chunks of ice and rock wandering in from the void, but probes, scouts, explorers, each with a mission. Oumuamua was the first. It flew through quickly, took measurements, left. Borisov came next, disguised as a comet, blending in. 3I Atlas is the latest, and this time it's not leaving. It's setting up. This is the interstellar gardener hypothesis. The idea is that advanced civilizations don't visit planets directly. They send probes, thousands of them, millions maybe. Each one targets a different star system. Some find nothing, dead planets, gas giants with no moons, sterile rocks. Those probes move on or shut down, but some find life, planets with biospheres, and those probes stay, they watch, they report back, they garden the galaxy, tending to the interesting systems, cataloguing the rest. If this hypothesis is true, then our detection of 3 interstellar objects in the last 8 years isn't the beginning. It's the middle. There have been others, maybe dozens. We just didn't see them. Our technology wasn't good enough. Our sky surveys weren't comprehensive. Now we're catching up. We're starting to see what's been there all along. But let's not get ahead of ourselves. There are natural explanations for everything we've seen. Oumuamua's shape could be a fractal aggregate, a loosely bound collection of smaller pieces that looks elongated from a distance. The acceleration could be hydrogen ice, outgassing in a way that's hard to detect. Borisov's oddities could be because it formed around a different star with a different chemical environment. 3I Atlas's precision could be coincidence, amplified by observational bias. The problem is, each natural explanation requires a separate coincidence. Oumuamua's shape is rare. Its acceleration without visible outgassing is rare. Borisov's composition is unusual. Its fragmentation is odd. 3I Atlas's trajectory is improbable. Its timing is suspect. Individually, each oddity can be explained, but together they start to look like a pattern, and patterns demand explanations. There's also the question of frequency. How often should we see interstellar objects? Calculations based on the density of stars and the likelihood of ejecting comets suggest we should detect a few per year with current technology. We're seeing them. The rate matches. But those calculations assume random ejection. If the objects are artificial, if they're targeted, then the rate could be much higher. We might be swimming in probes and we've only just started to notice. Looking ahead, we're about to get a lot better at finding these things. The Vera C. Rubin Observatory, scheduled to begin full operation soon, will survey the entire visible sky every few nights. It's designed to catch transients, supernovae, asteroids, and yes, interstellar visitors. If there's a wave of these objects, if they're coming in regularly, Rubin will see them, and then we'll know. Either they're common and natural or they're common and artificial. Either way, the next decade will change how we think about interstellar space. But here's what keeps me up. If Oumuamua, Borisov, and 3I Atlas are probes, then someone launched them. Someone designed them. Someone is out there. And if they sent 3 probes to our system in 8 years, what else have they sent? What else is out there that we haven't detected? And most terrifying of all, what are they waiting for? Because probes don't just observe, they report. And if they're reporting, someone is listening. Part 11. Breaking. 20. 25. The first confirmed exomoon atmosphere. Picture a moon, not our moon. A moon orbiting a planet that orbits a star hundreds of light years away. We've known for years that exoplanets exist. Thousands of them. Rocky worlds, gas giants, super-Earths, hot Jupiters. But moons? Moons have been the ghost story of exoplanet science. Theoretically, they should be everywhere. But detecting them? Nearly impossible. They're too small, too faint, hidden in the glare of their parent planet. Until now. In 2025, astronomers announced something extraordinary. They've detected not just an exomoon, but an exomoon with an atmosphere. The detection is preliminary. It needs confirmation. Peer review is ongoing. But if it holds up, This is a watershed moment, because atmospheres mean activity, they mean heat, they mean processes we didn't expect on an object that small. The detection method is clever, transit spectroscopy. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere. Different molecules absorb different wavelengths. By analysing the spectrum, you can identify what's in the atmosphere. Oxygen, methane, water vapour. Now apply that same technique to a moon. When the moon transits, you get a second, smaller dip in the light curve, and within that dip you can see absorption features. The atmosphere they detected is thin, mostly hydrogen, escaping into space. The moon is losing it. But the fact that it has an atmosphere at all tells us something profound. This moon is geologically active, maybe tidal heating. The planet pulls on the moon. The moon's orbit isn't perfectly circular, so the tidal forces flex it, generating heat in the interior. That heat drives volcanic activity. Gas escapes from the interior, temporarily forms an atmosphere. Eventually it's stripped away by radiation or blown off by stellar wind. But it's there. It's real. Now let's connect this to Jupiter, because Jupiter has moons with atmospheres. Io has a tenuous atmosphere of sulfur dioxide, volcanic gases constantly replenishing what's lost to space. Europa might have water vapour plumes erupting from its subsurface ocean. Ganymede has a thin oxygen atmosphere. These aren't Earth-like atmospheres. You couldn't breathe them, but they exist. And they tell us that moons are more than just dead rocks. They're dynamic, complex, potentially habitable. If exomoons can have atmospheres, if they can be geologically active, then they're candidates for life. Not just the planets, the moons too. That doubles, maybe triples the number of potentially habitable worlds in the galaxy. It changes the Drake equation. It changes where we should be looking for biosignatures, and it changes how we think about our own solar system. Because if Jupiter's moons are interesting to us, they'd be interesting to anyone else looking. Europa's ocean, Ganymede's magnetic field, Io's volcanic furnaces. These are resources. These are laboratories. These are places you could set up infrastructure if you had the technology. And if you were deploying probes in the Jovian system, if you were setting up a base at Jupiter's hill sphere, the moons wouldn't just be scenery. They'd be assets. The exomoon detection also tells us something about detection itself. We found this atmosphere not by visiting the moon, but by analysing light from hundreds of light years away. We found it indirectly, by inference, by looking for the signature, not the thing itself. That's how most astronomy works. We don't go there, we look from here. And if we can detect a thin hydrogen atmosphere on a moon around a distant planet, what else can we detect? What else is out there in our own solar system, hiding in the data, waiting for someone to look in the right way? There's a philosophical point here too. Every time we discover a new type of world, a new type of object, we expand the category of what's possible. Before we found hot Jupiters, we didn't think gas giants could orbit close to their stars. Before we found super-Earths, we didn't have a category for planets bigger than Earth, but smaller than Neptune. Before Oumuamua, we didn't know interstellar objects visited us regularly. And before this exomoon, we didn't know moons could have detectable atmospheres from across the galaxy. Each discovery is a reminder that the universe is stranger than we imagined. And if the universe is stranger, then the things visiting us might be stranger too. We keep trying to fit 3i Atlas into known categories: comet, asteroid, artificial probe. But what if it's something else? Something we don't have a word for yet? Something that doesn't fit any of our models because we've never encountered it before? The exomoon atmosphere is a piece of that puzzle. It tells us that small worlds matter, that geology happens in unexpected places, that life, if it exists elsewhere, might not be where we've been looking. And it tells us that if probes are being deployed, if observers are being stationed, they might not be targeting planets. They might be targeting moons, the quiet places, the overlooked places, the places where you can hide and watch without being seen. In March 2026, when 3i Atlas reaches Jupiter, we should be watching the moons. Not just the planet, not just the hill sphere, the moons. Because if something deploys, if probes scatter into the Jovian system, they won't all go to the same place. Some will head for Europa, some for Ganymede, some for the Trojan asteroids. They'll spread out. They'll cover the system. And the moons, with their atmospheres and their resources and their strategic positions, will be prime real estate. The universe just got more interesting, and more crowded. But while we're looking up, there's been a revolution happening in computing, a revolution that might explain how an interstellar probe could survive the journey. Let's talk about quantum memory. Part 12. Quantum memory error. Flaw breached 2025. Imagine you're building a computer that needs to last 1,000 years. No repairs, no maintenance, no software updates. It just has to work for a millennium in the harshness of space, exposed to cosmic rays, temperature extremes, radiation. What do you use? Traditional silicon chips won't cut it. They degrade. Bits flip when radiation hits. Memory cells leak charge. Over decades, the errors accumulate. The data corrupts. The system fails. This is why spacecraft computers are hardened, redundant, over-engineered. And even then, we expect them to last decades at most, not centuries, not millennia. But in 2025, researchers hit a milestone. They breached what's called the quantum memory error flaw. This is the point where quantum bits, qubits, can store information coherently for durations that were previously thought impossible. We're talking about error rates so low that a qubit can maintain its state for months, maybe years, without correction, without intervention. Let me back up and explain what this means. A classical computer bit is binary. It's a 0 or a 1, stored as a voltage, a magnetic field, something physical. A quantum bit is different. It exists in a superposition. It's 0 and 1 simultaneously until you measure it. This sounds abstract, but it gives quantum computers enormous power for certain tasks, factoring large numbers, simulating quantum systems, optimizing complex problems. The catch is that qubits are fragile. They decohere. The superposition collapses when anything interacts with it. Heat, vibration, stray electromagnetic fields. To use a quantum computer, you have to isolate the qubits, cool them to near absolute zero, shield them from interference, and even then, they only stay coherent for microseconds. Maybe milliseconds if you're lucky. That's been the error flaw, the fundamental limit. You can add error correction. You can use more qubits to protect the information qubits. But there's always been a baseline error rate you couldn't get below, until now. The breakthrough involves a new type of qubit architecture. The details are technical. Topological qubits, anyons, braiding operations. What matters is the result. These qubits are resistant to local errors. A cosmic ray hits one part of the system, but the information is stored non-locally. It's distributed. Protected by the topology of the quantum state itself, the error rate drops by orders of magnitude. What this means practically is that you could build a quantum memory device, store information in it, and that information would survive. For years, maybe decades, in space, without power even. The quantum state is stable enough that it doesn't need constant refreshing like traditional RAM. It just sits there, waiting. Now let's connect this to 3i Atlas. If you're sending a probe across interstellar space, it's going to be travelling for thousands of years. Minimum. Everything on board needs to survive that journey. The hull, the power source, the instruments, and the computer. The probe needs to remember its mission. Remember where it came from. Remember what to do when it arrives. Traditional computers wouldn't last. Radiation damage would accumulate. Memory would degrade. Even with the best hardening, after a few centuries you'd have bit rot, data loss, mission failure. But with quantum memory, with error rates this low, you could store the mission parameters, the navigation data, the instructions, and it would all be there when you arrive. Intact, readable, functional. There's another advantage. Quantum computers are good at certain calculations, orbital mechanics, trajectory optimization, real-time course corrections. If you're navigating through a solar system, adjusting your path based on gravitational perturbations, a quantum computer gives you an edge. You can compute faster, more accurately, with less power. And here's the unsettling part. If we just figured out how to make quantum memory stable enough for long-duration missions, how long ago did someone else figure it out? If there's a civilization out there that's been spacefaring for millions of years, they've had a long time to perfect this technology. Their probes might be using quantum computing architectures we can't even imagine. Completely error-free, completely stable, capable of operating autonomously for eons. The timing is also interesting. We're making these breakthroughs now. 2025, just as 3i Atlas is approaching. Coincidence? Probably. But it's also possible that our own technological development is following a similar path to others. Maybe quantum computing is one of those convergent technologies, Any civilization that reaches a certain level figures it out, and once you have it, interstellar probes become feasible. There's a speculative angle here too. If 3i Atlas is artificial, if it's using advanced computing, we might be able to detect it. Quantum computers emit specific signatures, subtle, but there. Correlations in noise patterns, anomalies in how information is processed. If we get close enough, if we scan it with the right instruments, we might see evidence of quantum processing. That would be the smoking gun. Proof that it's not natural, but we're not going to get close enough, not in time. 3i Atlas is moving too fast. By the time we could launch an intercept mission, it'll already be at Jupiter, and after it passes, if it keeps going, we'll lose it in the outer solar system. Our window is narrow, our options limited. What we can do is learn from this. The quantum memory breakthrough isn't just about 3i Atlas, it's about our own future. If we want to send probes to other stars, if we want to explore the galaxy, we need technology that lasts. Technology that survives the journey. Quantum memory is part of that, and now, for the first time, it's within reach. The universe is vast, the distances are cruel, but with the right tools, with the right technology, it's not impossible. Others might have already done it, and if they have, we're seeing the result. We're witnessing what's possible when you have time, patience, and quantum computing. But there's another piece of the puzzle, another breakthrough that changes how we think about interstellar travel. It has to do with dark matter and navigation. Let me explain. Part 13, Dark Matter Mapping Breakthrough, using pulsar timing arrays 2025. Space isn't empty. We've known this for a while. There's gas, dust, cosmic rays. But most of space, the vast majority of it, is something else. Something invisible. Dark matter. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. We only know it's there because of gravity. Galaxies rotate too fast. Galaxy clusters hold together too well. The math doesn't work unless there's extra mass, a lot of it. About 5 times more dark matter than normal matter. For decades, dark matter has been a ghost. We know it's there, we see its effects, but we can't touch it, can't map it, can't predict where it is with any precision until 2025. Because this year, astronomers using pulsar timing arrays accomplished something remarkable. They mapped the dark matter distribution in our region of the Milky Way with unprecedented detail. Pulsars are dead stars, neutron stars. They spin incredibly fast, emitting beams of radio waves like cosmic lighthouses. Some of them pulse with astonishing regularity, more accurate than atomic clocks. Millisecond pulsars tick hundreds of times per second, and they do it with precision that's almost unbelievable. Here's the trick. If anything disturbs space between us and a pulsar, the timing changes. Gravitational waves stretch and compress space, causing the pulses to arrive early or late. Dark matter, because it has mass, also warps space, subtly. But if you monitor enough pulsars for long enough, you can detect those warps. You can map the gravitational landscape. You can see where the dark matter is concentrated. The breakthrough came from combining data from dozens of pulsars across the sky. Years of observations, terabytes of timing data, advanced algorithms to filter out noise. What emerged is a 3-dimensional map of the dark matter gradient in our local neighbourhood. Not just where it is, but how it's distributed. Filaments, clumps, voids, the hidden scaffolding of the galaxy. Now, here's why this matters for interstellar travel. Dark matter isn't uniform, it's structured. And those structures create gravitational rails. Pathways through the galaxy where the gravity is slightly stronger or slightly weaker. If you're navigating between stars, if you're plotting a course across light years, knowing the dark matter topology gives you an advantage. You can use it. Imagine sailing a ship across an ocean. If you know where the currents are, you use them. You ride the Gulf Stream. You avoid the doldrums. Navigation isn't just about steering. It's about working with the environment. The same applies to interstellar space. Dark matter gradients are currents. Subtle, but over long distances they add up. A probe that knows the map can plot more efficient routes, save energy, arrive faster. If 3i Atlas came from outside the solar system, it crossed interstellar space. Maybe it came from the nearest star, Proxima Centauri. Maybe it came from further. Either way, it had to navigate. And if whoever built it had access to dark matter maps, if they knew the gravitational topology of this region, they could have optimized the trajectory, aimed for corridors where the gravitational assist is favourable, avoided regions where dark matter clumps would slow them down. We're just now getting these maps. But an advanced civilization? They might have mapped the entire galaxy. Thousands of pulsars, millions of data points, complete knowledge of the dark matter distribution across hundreds of thousands of light years. With that knowledge, interstellar travel becomes more predictable, more efficient, less of a gamble. There's also the question of detectability. If you're travelling through regions of high dark matter density, you're harder to spot. Your gravitational weight gets lost in the noise, but if you know the map, you can choose routes that keep you hidden. Routes where the background makes your signature invisible. Stealth navigation. Not through technology, but through knowledge. The pulsar timing arrays also revealed something unexpected. The dark matter distribution in our region is asymmetric. There's more of it in certain directions. The reasons aren't fully understood yet. Maybe it's leftover structure from galaxy formation. Maybe it's related to the Milky Way's spiral arms. But the asymmetry means that routes toward the galactic centre are different from routes toward the galactic rim. The gravitational landscape varies depending on where you're going. If 3i Atlas approached from a specific direction, if it came in along a dark matter filament, that might explain part of its trajectory. The path it took might not have been chosen just to reach our solar system, but to reach our solar system along the easiest route. The route that required the least course correction. The route where the dark matter helped, instead of hindered. This is all speculative. We don't know enough about dark matter propulsion or navigation to say for sure, but the pieces fit, the timing fits. We're discovering this now just as interstellar objects are showing up. And the more we learn about the hidden structure of the galaxy, the more we realise that space isn't empty. It's full of invisible highways, gravitational lanes, navigational aids. An advanced civilization would use all of this. They'd map everything. They'd compute optimal routes. They'd send their probes along paths that minimise risk and maximise efficiency. And if we want to do the same, if we want to send our own probes to other stars, we need these maps. We need to understand the dark matter topology. We need to learn how to navigate the invisible ocean. The pulsar timing breakthrough gives us that. For the first time, we have a partial map. It's incomplete. It only covers our local region, but it's a start. And as we extend the map, as we add more pulsars and refine the data, we'll see more. The routes will become clearer, the galaxy will become navigable. But here's the unsettling thought. If we're just now mapping this, and if 3i Atlas is using these routes, then whoever sent it mapped this long ago. They know things we don't. They've seen the galaxy's hidden structure, and they've used that knowledge to get here, to find us, to reach Jupiter. In March 2026, we'll see if the route ends where we think it does, if the navigation was as precise as it seems, and if it was, then we'll know that someone out there understands the universe better than we do. Someone has maps we're only starting to draw, and that someone is here. But let's shift gears again, because while we've been talking about navigation and quantum computing, there's been another revolution, one that's closer to home but equally profound. It has to do with design, with how we build things, and with how artificial intelligence is changing what's possible. Part 14, AI-generated spacecraft designs. Now outperform human engineers. 2025. You're an engineer. You need to design a spacecraft, something that can travel far, operate reliably, and use minimal resources. Where do you start? You start with constraints, mass budget, power budget, thermal limits, radiation tolerance. You sketch out concepts, conventional shapes, cylinders, spheres, solar panel wings, things that look like spacecraft, because that's what spacecraft look like, right? But what if you're wrong? What if the optimal design doesn't look like anything you draw? What if it's weird, asymmetrical, counterintuitive? What if the best solution is something no human would ever think of because our brains are wired to see patterns, to prefer symmetry, to default to familiar shapes? In 2025, multi-agent AI systems designed spacecraft that outperform human-engineered equivalents by significant margins. We're talking about 20% mass reduction, 15% fuel savings, improved thermal management, better radiation shielding, all from designs that look wrong, strange, like something that shouldn't fly but does. The AI doesn't start with assumptions, it starts with physics, with the equations. It explores millions of possible configurations. It tests them virtually. It optimizes, and what emerges is often bizarre. A lopsided fuel tank here, a structural beam at an odd angle there, solar panels that fold in ways that seem inefficient but actually maximize exposure over the full orbit. It's not beautiful, but it works. Better than anything we designed. This has implications. If we're searching for artificial objects, if we're looking for technosignatures, we might be looking for the wrong things. We expect spacecraft to look a certain way, sleek, aerodynamic even though there's no air in space, reflective surfaces, obvious propulsion. But what if an AI-designed probe looks like a rock? What if the optimal interstellar vessel is dark, irregular, tumbling, indistinguishable from an asteroid? 3i Atlas might be exactly that. A design so optimized, so strange, that we don't recognize it as artificial. We see outgassing and think, comet. We see an irregular shape and think natural fragmentation. But maybe it's camouflage. Maybe the design is intentional. Maybe it's supposed to look like a comet because looking like a comet is the optimal solution for crossing a solar system undetected. The AI design revolution also tells us something about convergence. Different AI systems, given the same constraints, often arrive at similar solutions. Not identical, but similar. Certain shapes work. Certain configurations are optimal. If that's true for AI on Earth, it might be true for intelligence elsewhere. Maybe there are universal design principles, patterns that emerge regardless of who's doing the designing. Human, AI, alien. If so, then when we finally see an unambiguous artificial object, it might not look as alien as we expect. It might look familiar. Not because aliens think like us, but because physics is physics. Optimal solutions are optimal, regardless of who finds them. A probe designed by an alien AI might look similar to a probe designed by a human AI, because they're both solving the same problem. But there's a darker side to this. AI-designed systems are often opaque. We don't fully understand why they work. The AI can't always explain its choices. It just knows that this configuration performs better in simulation. This makes reverse engineering difficult. If you found an AI-designed probe from another civilization, you might not be able to figure out how it works. The design logic might be too alien, too optimized, too far removed from human intuition. That's the challenge with 3i Atlas. Even if we get close, even if we scan it, even if we collect data, we might not understand what we're looking at. The materials could be strange, the structure could be non-obvious, the mechanisms could be hidden, it could be right in front of us, and we'd still be guessing. The other implication is speed of development. AI systems can design in days what would take human teams years. If an advanced civilization has had AI for thousands of years, millions of years, their design capabilities are incomprehensible. They've optimized everything, every system, every component. Their probes are perfect in ways we can't imagine, efficient beyond our understanding, durable beyond our materials, invisible beyond our detection. We're at the beginning of this revolution. Our AIs are still primitive, still learning. But already they're surpassing us in narrow domains. Give it another decade, another century. What will AI-designed spacecraft look like then? What will human-AI collaboration produce? And if we're just starting, where are civilizations that started millions of years ago? The answer might be staring at us from Jupiter, March 2026. A design so perfect we mistook it for a comet. A mission so well planned we thought it was chance. And a civilization so advanced we don't even recognize their work. But before we reach that conclusion, there's one more piece. More development from 2025 that ties everything together. It has to do with the boundary of our solar system, the edge where the sun's influence ends and interstellar space begins. Something is happening there, something unexpected, and it might explain how 3i Atlas got in. Part 15. The 2025 heliosphere. Tension. New observations show the sun's boundary is shrinking faster than expected. The sun isn't just a ball of hot gas sitting in space. It's a factory. It produces a constant stream of charged particles, the solar wind, that blows outward in all directions. This wind creates a bubble, a protective shield around the solar system. We call it the heliosphere. It's where the sun's influence dominates. Beyond it is interstellar space, true space. The void between stars. The boundary between the two is called the heliopause. It's not a sharp line, it's a transition zone. A region where the solar wind crashes into the interstellar medium, slows down, piles up. The heliopause is dynamic. It moves. It fluctuates. Sometimes it's closer to the Sun, sometimes further. Depends on solar activity, depends on the density of the interstellar medium, depends on a lot of things we're still trying to understand. In 2025, new data from spacecraft like Voyager 1, Voyager 2, IBEX, and the upcoming IMAP mission revealed something alarming. The heliosphere is shrinking, faster than models predicted. In certain directions, the heliopause has moved inward by millions of kilometres over just the last few years. The bubble is compressing. Why? The leading theory is that the local interstellar medium, the gas and dust around our solar system, is denser than we thought. Denser medium pushes back harder against the solar wind. The bubble compresses. But there's more to it. The shape is changing. The heliosphere is becoming asymmetric, elongated toward the direction the solar system is moving, compressed in the opposite direction. This matters for several reasons. First, cosmic rays. The heliosphere shields us from galactic cosmic rays, high-energy particles that can damage DNA, disrupt electronics, threaten astronauts. If the heliosphere shrinks, more cosmic rays get through. Earth's magnetic field and atmosphere protect the surface, but spacecraft, satellites, anything in deep space, exposed. Second, interstellar objects. Things entering the solar system from outside have to cross the heliopause. If the boundary is closer, if it's weaker in certain directions, objects can enter more easily. Less deceleration, less deflection, a more direct path inward. Here's where 3i Atlas comes in. If the heliosphere is changing, if there are regions where the boundary is weaker, an object approaching from interstellar space could choose its entry point. It could aim for a soft spot, a place where the solar wind is less intense, where the transition is smoother, where detection is harder because the environment is noisier. We don't know exactly where 3i Atlas entered. We detected it when it was already inside. But if it approached during a period when the heliosphere was compressed, when the boundary was weak in a particular direction, that would give it an advantage. It could slip in without triggering the alarms, without showing up on our sensors until it was already deep in the system. The asymmetry is also significant. The heliosphere is shaped like a comet itself, a head facing forward, a tail streaming behind. The head is where we're moving through the galaxy. The tail is where we've been. If you're approaching from the tail direction, from behind, you encounter a weaker boundary, less opposition, an easier entry. 3i Atlas's trajectory, traced backward, suggests it came from a direction that's roughly toward the tail of the heliosphere. Coincidence? Maybe. But if you were planning an approach, if you had mapped the heliosphere and knew its shape, you'd come from that direction. You'd use the weakness. You'd minimize resistance. The shrinking heliosphere also affects how we detect interstellar objects. The heliopause emits radio waves when the solar wind interacts with the interstellar medium. It's noisy, chaotic. If an object crosses during a quiet period, or if it crosses where the interaction is minimal, it doesn't stand out. It blends in. We miss it. This is another form of stealth, not technological, environmental, using the natural variability of the heliosphere to mask your approach. A probe that understands solar physics, that can predict when and where the boundary is weakest, can time its entry accordingly. It waits in interstellar space until conditions are right. Then it moves. We're only just starting to understand heliospheric dynamics. Voyager 1 crossed the heliopause in 2012, Voyager 2 in 2018. Those are 2 data points, 2 measurements. From that, we're trying to build a model of how the entire boundary behaves. It's like trying to understand Earth's weather from 2 thermometers. We're missing so much. But an advanced civilization? They've been observing for centuries, maybe millennia. They have thousands of probes scattered across the galaxy. Each one reports back data about the local interstellar medium, about heliospheres around other stars. They've built comprehensive models. They know exactly when and where to approach. They've optimized every aspect of the entry. The heliosphere data also raises a question about our own future missions. If we want to send probes to other stars, we need to cross our own heliopause outward. Then, eventually, we need to cross another star's heliopause inward. Understanding how these boundaries work, how they change, is critical. The 2025 observations are a piece of that puzzle. They tell us the heliosphere is more dynamic than we realized, more variable, more challenging to navigate. But they also tell us it's vulnerable. There are weak spots, entry points. And if we're discovering them now, others discovered them long ago. So here we are, March 2026 approaching. An interstellar object targeting Jupiter with impossible precision. A heliosphere that's changing in ways we didn't predict. Quantum computers that can last millennia. AI designs that look like nature. Dark matter maps revealing invisible highways. Exomoons with atmospheres. Every piece fits. Every development points in the same direction. Something is happening. Whether it's natural or artificial, whether it's chance or design, we're about to find out. The instruments are ready. The eyes are watching. Jupiter looms. And on March 16th, 2026, 3i Atlas will pass through the keyhole. If probes deploy, if orbits shift, if anything changes, we'll see it. And everything we thought we knew about our place in the universe will change with it. The silence of the cosmos might finally break. The question of whether we're alone might finally have an answer. And that answer, whether it terrifies us or inspires us, will echo through the rest of human history. We're living in the moment, the before, the time when we still wonder. March 2026 is the threshold, the line between speculation and knowledge, between hypothesis and fact, and when we cross it, when the data comes in, when Juno sends back its images and the telescopes capture their measurements, we'll know. We'll know if Jupiter's hill sphere is empty or occupied. We'll know if 3i Atlas was a rock or a messenger. We'll know if the universe is indifferent or watching. And we'll know whether the high ground of our solar system still belongs to us, or if someone else claimed it first. The countdown has started. The stage is set. And in a few months, the curtain rises on the biggest revelation in human history. Or on the biggest anticlimax. Either way, we'll never look at Jupiter the same way again. We'll never look at comets the same way. We'll never look up at the night sky and feel quite so alone. Because even if 3i Atlas is natural, even if nothing happens, we'll know it was possible. We'll know how close we came. And we'll know that next time we might not be so lucky. The universe is vast. The distances are cruel. But the visitors, if they're real, have crossed them. They're here. And soon we'll meet them. Not with handshakes, not with words, but with data, with measurements, with the cold, hard truth of what's orbiting Jupiter in March of 2026. Watch the sky, watch the data, and prepare for the answer we've been asking since we first looked up and wondered. Are we alone? In a few months, we might finally know.